Okay, let's get started now with some concepts that are fundamental to the special theory of relativity. And in fact, as you can see here, events, clocks, and observers, they're almost trivial in a sense, and yet part of Einstein's great genius was to look at some of these key concepts that most people had just taken for granted and look at them in a new way and say, there's something here we really need to think more deeply about. And so that's what we want to start doing here. Remember, as we talked about in a previous video clip, that learning, gaining new knowledge is like a construction process. So what we're doing here is really laying those solid foundations. And even if you think, this is just pretty easy stuff, it's trivial, it's important to make sure we get those foundations laid firmly, because in my experience, if you don't do that, later on you'll encounter some things that won't quite make sense, and you'll suddenly realize, my foundations of my knowledge edifice, as it were, I'm working up here on the 5th floor, and all of a sudden I realize, the first floor, the basement maybe, isn't quite as solid as I thought it was. So, events, clocks, and observers. And another principle will follow here. You may remember from one of our previous video clips is festina lente, Latin for make haste slowly. So we're not going to try to speed along here. For those of you who think maybe we're going a little too slowly, certainly you can fast forward to through these parts and get to the end of it. But again, I'd encourage you not to assume too much. Just make sure that you really have that solid knowledge that we need. So, events, clocks, and observers, part 1 of this. We want to start by asking the question, what does it mean to observe something? And in particular, obviously, we could observe something and you could write down everything you see. We're going to focus, though, on two things. Basically, where something happened and when something happened. Okay? So we want, if there's a given event, and our standard event will be like a flash bulb going off or some sort of flash occurring at a particular location and time, and we want to specify that location in space and in time. And so typically, we talk about a three-dimensional coordinate system. And don't worry if you haven't had this for a while, we're not going to do too much in 3 dimensions, but we want to do the general case first, and then we'll do simpler cases as we go along. But if we were going to create a 3-dimensional coordinate system, trying to draw it on a 2-dimensional board, we typically draw it like this, where we say this is the x-axis, the y-axis, and the z-axis. And clearly we need some sort of measuring system. We won't go into the details of how you might construct such a system, but obviously we have things like this, meter sticks or yard sticks, inches, meters, millimeters, centimeters, whatever, for our measuring system. And so in this case, we have the y-axis and the z-axis, and then the x-axis we have to imagine actually is coming out of the board here. And so we can specify any given point in that 3-dimensional space. If we put some tick marks on our axes here, we won't actually number them in this case, but here are the x tick marks. And then any given event would have an x-coordinate, a y-coordinate, and a z-coordinate. And so we could specify maybe the x-coordinate is 1, 2, 3. And so we'd come over here and maybe right here, and the y-coordinate 1, 2, 3, 4. And so, actually really looks like this. I went a little too far there. Okay, so that would be x-coordinate 3, y-coordinate 1, 2, 3, 4, and then maybe the z-coordinate someplace way up here, and this is where we have to use a little bit of our imagination to imagine it in 3 dimensions. So there is our event. So this is, here's the xy plane, and then some event with some z-coordinate in the vertical dimension there. Okay, so we talk about an event happening at x, y, and z. Clearly, though, we talked about not only where it's happening, but when it's happening. And so we need a time as well, and that's where clearly we have to have a system of time keeping. We we've got our typical clocks that we have standard time with. And again, we're not going to go into the details of how you create a timekeeping system. We'll just assume that we have one and it works pretty well. But for any given event, not only the location where it happens, but when it happens. So in fact, in addition to x, y, and z, we have one more coordinate to specify, and that's the time coordinate, t. And by the way, this is where the idea of time as the fourth dimension, which you hear about in a lot of science fiction movies and the like, actually comes from. It's not maybe as profound as it might seem to be in those science fiction movies. It's essentially just that we're marking an event, we're specifying an event with its three spatial coordinates, because we live in a three-dimensional world, x, y, and z, and then its time as well, what time it actually happens. Now, one thing this presupposes is we have an origin right here. And our origin is arbitrary. We could set the origin here. We could set the origin over here. Whatever system we set up, whatever coordinate system we set up, we'll specify some origin. For our purposes, usually the origin will be where we have an observer. So here's our observer. At the origin, this person then can mark off things in the x direction, y direction, z direction, obviously negative directions as well. I didn't draw those in because it gets a little messy on the board here. So they're at the origin. They are at point. You could say the origin is point x equals 0, y equals 0, z equals 0, and also time equals 0. That would be the time origin as well. So that really gets to the question of, how do we measure time here? How do we measure the time of this? Say there's a flash here. We'll just say it's some sort of flash bulb that goes off at that point in time. And maybe it's not, obviously it's not at 0, 0, 0. We said it was x equals 3, y equals 4, z equals 5 or so, something like that. So it'd be 3, 4, 5. And then at some given time, how are we going to record that time? Well, we could imagine that the observer here has a clock at the origin, a clock that keeps good time and is synchronized to some timekeeping system. And therefore, when that flash goes off and the observer sees that flash, they could record the time on their clock. There's a little bit of a problem with that, as you probably immediately see here. Something that you may know about, we haven't officially covered it yet, but light does not move at infinite speed. It moves at a finite speed. So when this flash goes off here, and let me see if I've got my red pen in here someplace. Well, we'll try green a little bit here. So it's green light in this case. So the flash the light from that flash takes a while to get to where our observer is at the origin. And so they record the time on their clock at that point, but clearly that time is a little bit after when the flash actually occurred. And clearly we could figure out what this distance was. Light moves at a constant velocity. Again, something we haven't officially covered yet, but you may know that. We will just assume it for the moment, that we know what the speed of light is. If we know the x, y, and z coordinates, we can figure out this distance here. It's really just the Pythagorean theorem really in 3 dimensions, which we won't bother with, but if you're interested in that. So we can figure out this distance. We could figure out, given the time recorded at the origin, we could backtrack and figure out exactly when it occurred here. So that clearly would be one way of doing this. But there's actually another way we're going to do, or actually let me just mention 2 other ways. One we'll use and one we won't. We could say, just to make things easier, why not put the clocks all over the place? In other words, why not have every point in our 3-dimensional space have its own little clock by it? We'll assume we can do that. They're imaginary clocks here. So that when this flash goes off, there's actually a clock right there. So we can record not only the x, y, and z coordinates, the 3-dimensional coordinates, but the time. In fact, we're going to call this a principle, and we'll call it the photo clock principle. the photo clock principle, or sometimes we'll just say the clock principle. Here's the idea. We're going to imagine that every single point in time has a clock associated with it. And all we have to do to find out when something happens, okay, we'll just see the flash of light, our standard event that we're using here, and we'll assume that when that flash of light goes off, there's a photo taken along with the clock time. So this is just a time clock, and photo taken, it records the location of the clock, the XYZ location, and the time that is showing on the clock at that instant. So we'll call that the photo clock principle. You might say, well, that's pretty common sense in a way, and what's the big deal about that? Well, we'll see this is going to be a really key idea when we work with some of the principles and results of the special theory of relativity. So that's why we're introducing it now. Again, to summarize, we're going to record an event, its location in space and time, where and when it happened, not only with its XYZ coordinates, but with a clock located right at those X, Y, and Z coordinates. So we'll assume that every XYZ point in our three-dimensional space has a little imaginary clock right there, and we can record that time. So really, you imagine, we'll sometimes call it a lattice of clocks, or sometimes we'll call it a grid of clocks. We use those terms interchangeably. So a lattice of clocks, you can imagine this three-dimensional space, and every single point has a clock associated with it, or so it's a lattice of clocks, or this grid of clocks, so that for any given flash that may occur in our three-dimensional space, we just look at the nearest clock there that will take its picture and record the XYZ coordinates and the time showing on that clock at that instant of the flash. Now, for those of you who might be saying, well, there are an infinite number of points here. We're going to have an infinite number of clocks. In principle, we could, but we'll just say that depending on how precise we want our timekeeping to be and our XYZ coordinates to be, we can also make the clocks closer and closer together. So again, these are imaginary clocks. And we'll just assume that we have enough clocks at enough points in space, and they're close enough together to record the where and when, the space-time location, the XYZ coordinates, and the time of any given event that we want. So that's the idea of an event. It's just we wanted to look at the where and when, the space and time location of the event. What that means then is to observe an event, and we'll often talk about observing an event, seeing an event happen. For our purposes in this class, what that will mean is we will record it using the photo clock principle. In other words, there's a clock, an imaginary clock at that point that we know its XYZ coordinates of that clock, and then flash photo goes off, it records the time, and that will give us the XYZT coordinates of a given event using the photo clock principle, or sometimes we'll just say the clock principle for that. Okay, so that's the basic idea of an event occurring, how clocks come into it, this lattice or grid of clocks. What an observer is, again, the observer is at the origin here, but the observer has their whole lattice and grid of clocks. And you could say, well, when the event actually occurs, they actually haven't seen it yet. The light hasn't reached them if it's far enough away. Even if it's not that far away, technically it hasn't reached them yet. Light goes very fast, of course, so essentially for common day experiences and events, it's nearly instantaneous, or instantaneous as far as we can tell in our everyday experience. But what does it mean to observe it? What it means for this observer is the flash goes off, the clock takes the photo of it, there's a photo taken of the clock, and then the observer can go back later and look at the recording of that and say, okay, it happened at XYZ, those coordinates, and time t. So that's what it means to observe an event. We will use this clock principle to do that. Now, having said all that, we've glossed over one point. I'm sure many of you are thinking, well, wait a minute, what about the fact of synchronization, or the challenge of synchronization here? We've got this whole lattice grid of clocks all over the place at every given point we're interested in here. How do we know they're all synchronized with each other? And so that's going to be our subject of our Part 2 video clip on events, clocks, and observers.